Welcome to this session of Shadow the Scientist. And we have our two stellar astronomers right here. I'm actually joining you live from the Keck Observatory headquarters in Waimea or Kamuela, Hawaii. And we have Bryce Bolin and Laura-May Abron here using the amazing 10-meter Keck 1 telescope. So we're going to be looking at, and actually already are looking at, if you're looking at the screen, bottom left, you can already see that they are on sky and have been for a few hours now. Right now, we're looking at trans-Neptunian Trojans, and we will explain what that is. But first, a quick introduction, starting with Bryce.
Hello, everyone. My name is Bryce Bolin. I am a research scientist at Eureka Scientific, and I am studying asteroids and comets of the solar system. Tonight, we are going to be studying very distant objects far from the sun, which is another one of my areas of expertise.
So, Laura-May, introduction.
Hello. I work at Griffith Observatory. I am helping out on these observations. What else? We did Three Eye Atlas at the very end of the night last night, which was awesome. Sorry, we can't run these for 6 hours. People need to sleep, I guess.
Yes, this is.
And we just did a main belt asteroid earlier. We had to redo an object from last night because it was sitting on top of a star. And so now we are going through the Neptunian Trojans, which is pretty exciting. And the scene's actually pretty good. And also we're lucky with regards to the weather. The observers for the rest of the weekend are not going to be as lucky. We squeezed in right before the weather gets bad.
Yeah.
So we're very, very lucky. The next few days are going to be rainy and cloudy here.
Oh,
So, hope we get the best that we can, especially since this is technically a reschedule of being clouded out on previous runs.
oh, I see.
So observational astronomy means that this happens sometimes. So you might join a session like this and see that we're entirely clouded out and we're like, okay. Or you do sucker hole astronomy, go right through in between the little clouds. We did that once, I think, when we were at the summit on IRTF.
Yeah. Ava, do you want to introduce yourself?
Hi, my name is Ava. I work at software here at Keck. So I'm just watching the observing process tonight.
What are you hoping to get out of watching Bryce and Laura-May?
I just want to learn a little bit more about how we can make observing easier here at Keck.
All right. And is that part of your role, making the observing process easier for the PIs?
Yes.
Amazing. Thank you for joining us, Eva. We are at the Keck headquarters in Waimea. This is a remote control room where observers can come. They don't have to go to the summit, but they can do everything from right here. So pretty special to be able to join them here today. All right, and so I see you all in the chat, and we already have some questions. Okay, so welcome, Rob, Vani, Lucille, Annalise, and those of you on YouTube as well. So your questions and comments are welcomed here in the chat anytime. So Bryce, Laura-May, and the bottom left here of the screen, we have this nice black and white image. What are we looking at here, and what are those striations kind of on the right-hand side?
So this is this right here. So we just changed the filter, but this is a 182nd exposure J-band image. So we're talking about 1.25 microns ish, somewhere around in that vicinity. And this is a product of 18 separate 10-second coads. So because the sky is so bright in the infrared, you have what we call saturation of the detector if we expose the camera for too long. So we have to take short exposures and we have to coad them together in order to build up the signal. And so what this is, this image right here was created by adding 18 10-second exposures, separate 10-second exposures together. Now we just changed the filter. We're in the process of taking an H-band image, and that uses 3-second exposures. So we need to take 60 separate 3-second exposures and coad them together to make an image. But we're about halfway through the H-band image, so I can show you the J-band image. So if we zoom out, I'll show this is what the entire image looks like.
Ooh.
But this is one exposure. And it just so happens that at J band, you get a lot of emission from the sky and from the instrument itself, which decreases the sensitivity. So we apply a special technique that removes the background from the instrument and from the sky. And we typically do that by taking multiple exposures and dithering them together in order to remove all the stars to create a uniform background image. But as we're taking data, we don't have all the processing steps available to us. So we do what's called kind of a quick look. And so the quick look is just by subtracting the previous image from the current image. I can show you what that looks like if I press the tab key here.
Oh, yes, please.
It subtracts the two. So you can see that the before and after is quite striking. So here is the after and here's the before. So you can see the before, there's these patterns, there's some striations, and you don't see nearly as many stars. But when I subtract the two, a lot more stars pop out. Yeah, so this is sort of the power of a 10-meter telescope. Even though 180 meters isn't super long, it's 3-minute exposure time. It's pretty long, but it's not super long. But we see many, many more sources. When we subtract the two science images, the science images from each other, it really removes the sky background, and a lot of the fainter objects really pop out. Now, what we're looking for here is an asteroid. Now, it's kind of hard to find because there's so many sources on here. So I have a finder chart to help me. And I could see I think this is it right here. This asteroid from right here is closest spotted asteroid. I think the asteroid is right here. So I'm going to zoom in a little bit.
Oh, yes.
That's it right there.
Ah,
Zooming in on my
that's it.
cursor, so I'll draw a little line across it right there. This is a projection. There we go. So just to the left of this green line right here is our target asteroid right there.
Wow. Wow.
And so we did 5 J-band images. Now we're taking H-band. We switched to H-band. And so hopefully soon we'll have some H-band images we can show you.
Nice. And so what's the difference between the J and the H band?
So I'm going to send you a website link.
Yes.
Maybe that can help. It's okay if I text it to you?
Absolutely. And I will drop it in the chat. Yes, because there are, and in fact, you all, in this top left panel where my cursor is, you can see that so there's lots of different filters and there's lots of information going on. But kind of in the center here, you have imaging and you see all those letters Y, J, H, K. That's the band that they're using.
So do you want to show them the link I sent you?
Yes, let me grab it. Let's see where it is. Okay, got it. Okay, so I'm gonna
So we
put
just
this link in
pushed
the
H-band
chat.
image.
Okay.
Now it's taking the second one.
Okay.
Each of these takes about 400 seconds to do.
Okay. Got it. Okay. So let's drop that in the chat. Okay, so here's the link that Bryce just sent us to hopefully help us better understand. Yes, there we go. Yes, so take a click on that, and I'm going to actually do that right now on my other device. Oh, yes. Okay, so this table starts at the top with filters, and oh, there's a lot of information here. Okay. Yes.
So we're observing in 4 different filters. They're called Y, J, H, and there's another filter called the last filter is called K, but we were using a special version of the K filter called K short. which covers a little bit shorter wavelength than a regular K. But the wavelength coverage of the wideband filter is at around 1.05 microns, and J is around 1.25 microns. H is around 1.6, and K short is about 2.15 microns. So in total, we're covering a range between about 0.095 microns all the way out to about 2.3 microns. But this is a wideband imaging, so we're getting 4 images and four different types of images and 4 different filters.
Right.
So soon, we're about a third of the way through our second H-band image, and so hopefully that will reveal to us the object in H-band. We'll have a nice H-band image.
Ooh, yes. And in this top left panel, you can see the progress bar here at 38%, 39%. So it's getting there, getting there.
Slowly but surely.
Mhm. Yes. And so as Laura-May mentioned, she mentioned a term called seeing. Laura-May, could you explain the importance of seeing to us?
It's basically how good our image will end up being, just to make it really simple. You know, the sky in general has a lot of turbulence. Our upper atmosphere is kind of in the way of all these objects we're looking at. That's nice when you can observe things from the James Webb Space Telescope or the Hubble. You don't have seeing, obviously, because
That's
it's
true.
up above the atmosphere.
That's
and so
right.
you're always it's always perfect.
It's always nice. Always nice in space.
But from the ground, we have the atmosphere that protects us in the way, but it is in the way of our observations. And so seeing, just as it suggests in the word, is essentially how good we can see. And that is determined by turbulence in the atmosphere, atmospheric conditions, weather, things like that. Heat, humidity. Keep in mind, we're observing from the very summit up at 4,000 meters of a very giant telescope. And this is where it is actually the best sky on Earth, the best conditions on Earth, even better than Chile. I'm a big fan of Chile, but Maunakea is the best sky on Earth, best conditions. And so you want to have minimum humidity, minimum turbulence, and that is found on top of this mountain and very, very few other places on Earth, unfortunately. We could put telescopes in lots of places, but it's hard. The conditions here are incredible.
Yes, yes, they really
And
are.
when you're looking at things that are very, very faint, keep in mind these are out near Neptune. This is 30 astronomical units away. So 1 astronomical unit is the distance between Earth and the Sun. So that's 150 million kilometers or 93 million miles. And you're looking at 30 times that distance for an object that is far, far dimmer than the Sun, than planets and things like that. And so you really want to have good seeing because you're looking at these tiny little pixels. And even though this is one of the biggest telescopes in the world, it really does matter.
It really does matter.
So we love good seeing.
Yes. Good seeing is important. Okay, so one of the things that we did yesterday as we looked at some different Trojans, and I see in the chat we already have a question about the Earth co-orbitals. We did look at a few. I think one yesterday. Did we look at one of the co-orbitals last night?
We didn't get
We
to
did
it.
not get to
We
that.
might do it tonight.
Okay.
We'll see.
Yes, we'll see. I'm not sure that's going to be during our session, but if I'm able to capture any images during later after we end the session, I'll still be recording. Yes, and so if we capture anything, I'll be sure to send that portion to you all because it's so cool. There's a new mini moon just from the beginning of the year already, a new captured mini moon. So that was
We
the
are
target.
just about to get our second H-band image. Let's see how this turns out.
Let's check it out. H-band image.
Here we go. So this is before, and we'll do zoom scale frame after. So we'll do it again before, after.
Ooh.
So
It is.
before, and this is the after. So there's some little noise right here, but let's see if we can zoom in and find our asteroid without looking at a binary chart.
It's early enough in the night.
Yes.
I think this might be it.
Okay, so you see the cursor in the
That's it
bottom
right there.
left pane. That's it.
That's it right there.
Yeah,
looks
there
like
it is. You can see it.
I don't know if do you have Aladdin open? Otherwise, I don't know if you can see it on the screen, but we're
Oh,
I have
looking at
thank
Aladdin.
you.
Do a little comparison, and I don't know if they know what an asterism is.
Oh, but tell us what an asterism
It's
is.
basically like a little group of stars, so a little made-up constellation. The most famous asterism is the Big Dipper.
It sure is.
Big Dipper is not actually a constellation. It is part of Ursa Major, which is a much larger constellation. But we
Yeah.
don't often see those other stars. They're much fainter. So we just see that kind of, I was about to say it in French, casserole. We call it a pan.
Oh, man.
And I guess you guys call it a dipper. In some places it's called a like a plow also.
Yes, the plow
So
and
different cultures have a different, I don't know if, well, I guess, yeah, here you can't see it. I would guess.
can't see what.
Oh, you can
Big
see the
Dipper?
big
Can you
dipper.
see it?
Oh, yes, absolutely.
Okay.
Yeah,
I'd have thought we
It's
were
just
first
lower.
Yeah, it's lower.
yeah, but we.
You can see all circumpolar stars.
That's right.
So
Mhm.
everything up to the North Pole.
But yeah, so you want to look for your asterism. You're kind of looking at like, ooh, what line or recognizable group of stars can I find on these catalogs in that region
Right.
and compare it to the image we're getting to find something that's there that we don't have in our catalog image, and that's your asteroid.
That's it.
Does that
Asteroid
sound very
hunting.
easy?
Oh no.
And the Vera Rubin will be amazing. If you've heard about the Vera Rubin coming online, new telescope in Chile,
Yes.
it is doing a new catalog basically, and that catalog will be much deeper. And so it will have a lot more objects in it, which means that when we're comparing our image from the catalog to the image we have on screen, it's going to be much easier because there are some things that appear on our screen that we don't have in our catalog. It couldn't
Right.
be things that were that faint. And so the Keck is very powerful and can see much fainter objects. And so we want a full catalog. And so the Vera Rubin will deliver that, and we'll be able to have really accurate comparisons, which will make it a lot easier to find these objects and discover new ones too. That'll be
Yes.
exciting.
It will be. Definitely. I'm gonna put a link to the Vera Rubin, Vera C.
Do you
Rubin
think that
Observatory.
Vera Rubin's going to find more Neptunian Trojans?
Oh yeah, sure. We're hoping so.
Yeah.
It could be, I think, tens of thousands that are about a kilometer in size or more.
Wow.
Yeah,
I
they're
think I'm seeing
expecting that they'll
estimated.
find a few hundred of these. But the
Yeah.
Rare Rubin.
And we only have about 30. So
That's
Right. Right.
very far, very faint.
Far and faint. And what about what size are these? And when you talk about faintness, the magnitude also. So they're small and what 20, 22,
Like 20,
right?
23rd
22,
magnitude.
yeah.
23rd
Which sounds bright, but in the infrared that's quite faint.
Yeah.
Okay.
I think when we observed Wire 4 last year, which is not a Trojan,
That's right.
that was the famous asteroid that maybe was going to crash into Earth, but it's not going to crash into Earth. Might crash into the moon though. And now we observed it at like 24 mag or something. It was really,
Oh,
really
Yeah,
faint.
it was pretty faint.
I think we were the last Earth-based observations of it.
Yeah.
Oh, really?
Because it
Wow.
was so faint. I mean, that's really pushing the limits of these telescopes.
I'm so glad you brought that up because 2024 YR4 this past week here on the Big Island in Hilo, we have a program that is kind of led by the International Gemini Observatory called Journey Through the Universe. And a student in I believe it was the 5th grade class, either it was a 5th or 6th grade class, in fact, asked me about if that asteroid that we found a few years ago if it was going to hit the moon, and I
Yeah.
didn't remember which one it was, but I said, yeah, I think there's like a 3 or 4% chance that it might in what, like 2030, 2032,
Something like that.
something like that. Yes, yes. So this was an elementary school student who is on top of the latest astronomical
It got a
news.
lot of press. I
did.
would say almost as much as 3i Atlas, because people were, constantly asking me about it. And I feel like it was just, even nowadays, people will still be like, oh, you know that asteroid that might hit Earth? And yeah, so it's 22nd of December 2032. It's the exact date.
Okay.
But yeah, there was a very cool presentation at AAS. AAS is our big conference, yearly.
American Astronomical Society.
American Astronomical Society. So it is the Super Bowl, the superb owl of astronomy, and it happened this year in Phoenix.
Sure did.
And Professor Martin Connors, he gave a very cool talk, talking about kind of analyzing a sweet spot, where if it lands on the moon in a particular way, particular time, then it could throw a lot of ejecta our way. But it's kind of a very narrow, but I don't know what the percentage calculated was, because I know that also he mentioned someone was trying to, I think, maybe get more James Webb observations of it. But yeah, but all that will be revised when there are more observations of it.
Absolutely. Absolutely. I heard exposure complete.
Yeah, we just got
Look at that.
got another one of these.
Ooh, look
Now
at
we
that.
gotta find the thing.
Okay, those of you in the audience, let us know in the chat.
Does anyone want
Let's do a contest.
Yes, who can find that?
Whoever finds it, you win our gratitude.
Yes.
I think I found it, but I want to give someone else the opportunity to spot it.
It is.
Spotted. Pun
It's
intended.
hard. Ah, nice.
Sky
Let's
is spotted.
see.
And we got
Okay.
black and white polka dots here.
That's right. Very 60s.
Ooh. I don't think I spotted it, but is that a galaxy kind of in the top right?
Not here. Yeah.
Yes.
Yeah, that's a galaxy.
Yeah.
Wow, there's so much. It's
You
so
usually tell the
bright.
difference, by the way, should I let you explain how you can tell it's galaxy?
Oh, please tell us.
Just the shape of them. They're not all, of course, these cute little, elliptical galaxies, but usually if you see that kind of smeared, that's an ellipse as opposed to a perfect circle. On some images, also, you can occasionally, other types of images, you can tell by the fact that it's got diffraction spikes. The little spikes coming off of the stars, but here we have much fainter stars. But yeah, galaxies, they're beautiful.
Okay, thank you. Let's see. Let me check the chat. Okay. Oh, no. Okay. No takers on trying to find that one in Bryce. Let's see. Where do you spotted it? Let's see.
Let's bounce off here. So let's play the constellation game.
So Bryce has opened a program called Aladdin that Laura-May mentioned earlier and was showing you. And so he's doing a comparison, looking at that image and then the one that they just got, to see what has changed, what is new in the image that they just got from Keck, to see if they can find it.
If you want, I can text you the coordinates.
Oh,
that we're looking at if they want to try it.
Yes, let's get the coordinates. Yes, Laura-May.
So you can access Aladdin online. You don't necessarily need to download it. You can just go on Aladdin Lite. So I'll send you the link right now.
Okay, thank you.
Send you the link. Drop in the chat.
All right, Aladdin Lite.
There we go.
Thank you.
And I will send you the coordinates.
Got it.
So you want to load the Pan-STARRS catalog? An excellent catalog, which the person next to us worked on.
I just worked on the asteroid finding asteroids in the individual Pan-STARRS image. I didn't help with the this nice colored image catalog.
But you contributed to
it's a very it's a very nice catalog.
It is.
And then I'm sending you now the coordinates. So once you have the Pan-STARRS opened, or the Aladdin Pan-STARRS catalog, You can punch in on the very top right these numbers that I just sent you, Jamaica, to drop in the chat.
Got it.
And this corresponds to our right ascension and declination. So this is essentially how we find objects in the sky. These are the celestial coordinates.
All
So
right.
it'll send you to the exact part of the catalog, and it should look similar. You'll be able to find some of the little asterisms and compare them to what we have on screen.
Oh, that is
All right.
so awesome. Yes. All right. So those are that link and the coordinates are in the chat. You'll let me know if you check it out. Okay. So Annalise, Joan, welcome, Joan. Oh, okay. And I forgot to ask this. I was so excited about what we're doing here. Please let us know where you're joining from. As I said, we are here in the remote control room here at Keck headquarters in Waimea on the Big Island of Hawaii. And I see we have some new people joining us who may not have heard that earlier. So welcome, welcome. And yes, please put in the chat where you're joining us from. Thank you. And those of you on YouTube, I know you can't really put anything in the chat to tell us where you're joining from, but in the metrics I can see that. So we're excited to have you here from wherever you're joining us from.
So I can kind of point out here where the asteroid is. So
Okay.
what we want to do is we want to look for common groups of stars here. So there's this big cluster right here that is very distinctive from all the other star patterns here. And then we follow it down to a little bit to the southwest. There's kind of a triangle right here.
Oh.
So there's this triangle right here, this kind of triangle shape.
Yeah.
And then we go a bit south of that, and then we find there is this trail of stars right here that kind of makes like this W shape. Oh, we just got a new exposure, so let's use the light.
It's almost like a little Andromeda.
I was thinking that. Yeah.
Right?
Yeah.
And so let's find it again. So we have the cluster up here. Let's follow a little bit south. And you have this kind of triangle right here. You follow it a little bit more south, and you get this trail of stars right here. And where the asteroid is kind of to the right of this trail. It's that little dot right there.
Oh.
Yeah.
Yes. Wow.
By the way, when you load those coordinates in Aladdin that he sent to you, it will put a little cross. So it will put a little pink cross as to where those coordinates are. And that's why it's somewhat a little easier. Once you find the asterism, you just check right there. And it should be somewhere there. So.
Nice. Let us know in the chat if you check that out. I mean, that is tiny, so tiny. I could barely see it even with your cursor and finger there.
Sometimes I think yesterday you were like, oh, is that a hot pixel or is that an asteroid?
Yes. Yeah. What's a hot pixel?
It's when your detector it's just a little can I call it an issue with the detector?
So most of these detectors work, they're photoreceptive. So the more photons that fall on a particular pixel, the higher the value. So the pixels store a numerical value that corresponds to the number of electrons that they receive. And so the electrons are produced by photosensitive type material. It's kind of like a photomultiplier too, but in silicon format. So when a photon falls on that little pixel, that little piece of the chip, it increases the charge on that part of the detector, and that charge is then converted to a numerical value. And so for a regular CCD, you're going to have a value between 0 and 65,000. So it's like what was that? 32-bit number there. So it's but this is a little bit different. Infrared's a little bit different. The maximum value, saturated value, is about somewhere in the 40,000s. And but a hot pixel is one that has its numerical value stuck on the maximum value. So if it were a regular CCD, it would be about 65,000. And in these infrared CCDs, it's about about 45,000.
It's outputting more electrons.
Well, it's kind of a glitch.
Yeah.
Mm.
As opposed to a dead pixel, and a dead pixel just means it doesn't function.
It's not.
And that happens in cameras quite a lot. If you have any
Yeah.
DSLR, like I know from some DSLRs I have that, there's areas where there's a dead pixel, and so when I have my picture, I just know that, especially when you have a lot of noise. So you're taking pictures at night, for example.
Sorry, 16-bit, not 32-bit. So the regular CCDs is 16-bit number, 16-bit integer, but these are much less than that. They're about 40,000 instead of 65,000.
So there's all sorts of things that can happen with your detector that are not part of the actual image. And maybe for other, I don't know, I'm trying to think of other sciences where it would matter, but I guess if you're doing astronomy, it's particularly annoying.
Yeah.
Everything you're looking at is like a little tiny dot. And so you're like, is that a star?
Yes. 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 All right. So Joanna, thank you. You are joining us. You're an undergrad student from Central California.
Yes.
Oh, you've always been interested in astronomy, but at a very amateur level. Amazing. Welcome. You're in the right place.
Well, maybe something we should do is explain a little bit, because we're good ways through, but we should explain what these different what's going on here.
Please.
The different windows here. Do you also want to link them the
Yes.
Subaru thing, because that's sort of a picture of the telescope.
Great suggestion. I'll do that while you're explaining.
So we're using an instrument called MOSFIRE, and which is on an instrument on the Keck telescope on Maunakea. And so the way we control the telescope and instrument are separated. So we have each of these different windows corresponds to a different function related to either the telescope or the instrument itself. So in the bottom right-hand corner here, this is the telescope controls, if you will. We don't have direct controls of the telescope. The observer, who is Tony, who's on the summit right now, is driving the telescope for us. Mm-hmm. But the way that we interface with the system that communicates with the telescope is in this bottom right-hand terminal right here. And so we have a list of our targets right here, and this thing is called the Magic Q. This is sort of the guide camera. So we have a list of our targets right here already loaded in as a kind of like an Excel spreadsheet. Mm-hmm. And we select our targets, and then we send them to the telescope system, and then the telescope observer is pointing the telescope for us, and they're also doing the focusing as well. They're doing a lot of the crucial functions for the telescope. We actually don't really touch the controls of the telescope, and that's by design for safety reasons. So I think we're almost done with our 5th exposure here, so I'm going to change the filter, and that's going to be instructive, because how we actually control the instrument is in this top left-hand corner here. So I'm going to change the filter to Hey Short, and so this is where I control the filter as well as the exposure settings on the instrument. So I just changed it to, we're going to change and do K-filter observations, and so we're going to use an integration time of 6 seconds, and I'll explain why we use such a short integration time. We're going to do 30 coads, so that each individual let's say image is about 180 seconds eye time. It's not really 180 seconds eye time, but it's somewhere in that ballpark. So I'm going to click apply, and I'm going to start the exposure sequence. So the controls for the actual instrument, the camera, are all right here. And so I have this terminal right here where I just send a command to it to tell it to take 5 exposures using a setup where we're going to take 30 6-second exposures and co-add them together. Now, another thing that we do, so right now, this is a special instrument that uses a chip. Can take individual spectra of multiple objects in the same field. So the field of view of the instrument is about 7 arc minutes across. So you can take a spectra of about a dozen or so different objects, all within that that field of view. Mm. I think you could take Eva, do you know how many spectra you can take in one shot with MOSFIRE? Is it somewhere 20 or 30 or so?
It all depends on what you're looking
Mm.
Yeah, it depends on what you're looking at, but you can do dozens of objects at a time, as long as they're all within a 7 arc minute distance of each other, and within a 7 arc minute field of view. And so the way you set that up is here. We're using the instrument in open modes because we're taking images. But if you wanted to take spectra, you would use this panel here to control the slit unit that sets up which observations are, which objects in your field of view have a spectroscopic slit on them. And that is called the controllable slit unit. And this is the interface for the controllable slit unit.
Mhm.
And so it's these two top screens that control the mechanics of the device, the actual devices in the camera itself. In this bottom left-hand corner here is where we actually look at the data. As a quick look of the data. So here we just finished. We're now taking our K image, but previous to taking the K image, we took a bunch of H images, and then we can kind of get a quick preview of the image. So in the infrared, we get a lot of background in the image from the instrument and from the sky, but we have a quick look method that can remove it. So this is the individual image. Then we have a way of subtracting the images from each other, and they're dithered, so the sources the stars and asteroids aren't going to be subtracted from each other, but the sky portion is. So I'm going to do that right now. I'm going to press tab. So this is, I'm going to give you a little bit of before and after. So this is before doing the sky subtraction, and this is after doing the sky subtraction. See, there's many more sources in there.
Yeah.
So it really makes things pop out. Now, the next thing we were doing before you joined us, we were playing Spot the Asteroid. So that's a little tricky, but you try to find asterisms, which are kind of like a little bit like constellations. Laura-May was explaining that before.
Mm-hmm.
And so we have two constellations that we're using to kind of keep track of where the asteroid is. So we have this cluster of stars right here that I'm circling with my mouse. Can you all see that?
Yes, we can see that.
And then there is this kind of triangle elbow shaped thing right here. And then south of that is this little line of asteroids, which looks kind of like a W. And the asteroid is right there. So I'm going to zoom in on that right there. So that's the asteroid right there. But I'll show you these step by step. So first thing you do is you find this cluster of stars right here. And then you go a little bit to the southwest or the southeast of that, because east is to the left on this image. So you go a little bit southeast and you find this triangle looking thing. And then you go south of the triangle looking thing to find this W right here. And the asteroid is right there, right?
Wow. Yeah. Oh, wow.
So we're about to finish our first K image, and that's great. We're making good progress here. So we will do that soon.
Also, the asteroid we're looking at, I think we're still on. Yeah, it is highly inclined. So it's inclined at, I think, just over 20 degrees, 22. So that means, if you consider the plane of the solar system, it's quite a bit inclined, even more so than Pluto. I think Pluto is 17 degrees inclination, I think. So a lot of these are highly inclined.
And that inclination, having a high inclination, does that mean it's from further out in the solar system and came in, or that it's been perturbed in some way?
My understanding, and Bryce can corroborate, is that is partly a sign of proving potentially migration of planets. Is that correct, Bryce?
Yeah. So so what we're looking at here, these objects they're called trans-Neptunian objects. It's kind of the blanket term, but these are a special type of trans-Neptunian object called the Neptunian Trojans. And what Trojan means in that, what Neptune means and what Trojan means in that term, Neptune means that these objects are in the orbit of Neptune, and Trojan means that they're in a 1-to-1 mean motion resonance with Neptune. So the most famous Trojans in the solar system are the Jupiter Trojans. That was what originally gave these types of asteroids the Trojan name. And what that means is that they share the orbit of Jupiter, but they're trailing ahead, or they're a little bit located a little bit ahead of Jupiter, or they're a little bit trailing a little bit behind Jupiter in its orbit. And they were given Trojan and Greek names originally when they were discovered. So I forget which side, but one side is only Trojan named, and on the Greek side, and then the other side is Greek and only Greek names from the Iliad.
That's right.
Characters from the Iliad. So there are asteroids like given a name like Achilles and Agamemnon and Hector and Eurybates, famous characters from the
That's right.
Iliad.
Wow.
But as we found more asteroids. So Earth actually has Trojans. It has only two. They're pretty rare. But anytime we define an asteroid that is in this kind of orbital configuration where it's a little bit ahead of the planet or trails behind the planet, we call that a Trojan type orbit. And Neptune is another planet that has Trojans. In this case, it's the Neptunian system, Neptune. So it has asteroids that trail behind it, as well as go a little bit quicker, located a little bit further along ahead of the planet Neptune. And these objects, we think that the Jovian Trojans and the Neptunian Trojans are captured populations, so that they actually were not formed there. They were not birthed in the vicinity of Jupiter. They were actually captured from somewhere else in the solar system. And we think that their inclination, they can have low inclinations as well as high inclinations. And we think that the reason why some of them have high inclinations is due to the fact that they were captured from some other population.
And if you, in fact, so where they are, L4 and L5, if you're familiar with, for example, the James Webb, the James Webb Space Telescope is at L2. So you have, for every body, you have these other points of balance, basically, where things can be in relatively stable orbit. And so where James Webb is kind of far away from Earth, behind it, and the L4 and L5, if you take the circle, the orbit basically of Neptune, they're kind of like adjacent, just along that circle before and after, as Bryce was saying. And so these are all points of balance, but we use those Lagrange points.
Yes.
We use them to put all sorts of satellites and instruments there because those are very useful places. But
So we're about to get we got our first K image right here. This is our first K image. We're about to get our second K image. And so what I'm going to do is I'm going to show you what that looks like.
Ooh, yes.
So we're going to play the game again, find the asteroid.
All right. And in the chat, I've put an article where Bryce was interviewed about the Neptunian Trojans, not only their quantity, but also it's about the color. There's some red ones. Take a look at that article. Let me know if you have questions. All right, we're ready for this next image in the key band.
All right, so we have here, we're going to do before and after again.
Oh, look at that big galaxy in the top left.
Yeah.
Really well.
Oh,
So
wow.
this is before and this is after. Great. So y'all want to look at the galaxy? So this is before and this is after. Y'all want to look at the galaxy?
Let's do it.
All right, here we go.
So pretty.
So we have to play with the scaling a little bit on the image to make it pop out. Let's see. It's kind of hard because it's an infrared image.
That's a nice galaxy.
That
That's
is.
a very bright galaxy.
The core is
There's
really.
another one on the right of it. You can
Yeah.
kind of see it back.
I see it. It's
Wow,
faint.
look at that.
See if I can make it pop out. It's kind of hard because it's an infrared image, so the way it's processed.
Ooh.
Wow.
So what I'm gonna
Wow.
try to play with the scale parameters here to make it pop out a little bit.
Ooh.
So if I do this,
Nice.
yeah, I can get the-
Oh, that is great. Wow, Bryce, that looks
Yeah,
amazing.
so you play with the stretch a little bit. So yeah, there.
Wow.
It's got some structure there.
Yeah, you can clearly see the spiral arms
Yeah.
there too.
Yeah.
There's another one.
And we don't know. I mean, these could be background. These could be foreground stars.
Yeah.
Not background stars. Foreground stars. Because these are stars in our galaxy, and the galaxies outside of our galaxy.
Right.
I'm not a galaxy expert, right? But they have like these gas clouds floating around them, and so they can have these clumps there. I'm not a galaxy expert, so I don't want to say they're it's not unusual to see clumps like this inside
I
a
see.
galaxy.
I see.
Now we are in K-band, so we don't know what we need a galaxy
Yeah.
for here to
Tell
talk
us.
with us. Maybe
Yeah.
Leo. If we
It's
have-
amazing how well you can see the structure on it, though.
Yeah,
It's
it
got a
is.
kind of a ring here, and then
Yeah.
Sure does.
So let's see if we can find anything else in here that's extended. I thought I saw another galaxy somewhere around here. Yeah, there's another.
Yeah,
one
there
right
is. Sure is.
Yeah, there's another-
Oh.
I can see that.
Oh yeah, you sure can see that nice and clear.
Yeah,
Oh yes.
yeah. Let's see, here's another one. Nice. Yeah, the galaxies.
Oh nice. Yeah.
If you ever want to play this game, go visit Griffith Observatory. If you ever go to Los Angeles in
There's
California, there's the largest printed image of space called the Big Picture. It was made at Palomar
Lots of
Observatory.
galaxies.
And there's tons of galaxies. It's on a
Ooh.
part of the sky that has the Markarian chain.
The Mercurial
Chain of galaxies that
yeah.
makes a very nice emoji face.
Oh.
We have little galaxies.
So let's find the asteroid real quick, just to make
Yeah.
sure
It's in there.
we are doing the right things here. So let's find it again. Now the stretch is different, so now we have to kind of reinvent things. But here is the star cluster right here that we were using.
Mm-hmm.
Here is that elbow, the elbow centered up here. That's the elbow. And then now we're looking for here it is, the chain, and there's the asteroid right there. The stretch is different. So when you're on this mode, so we're using the mode of DS9 to look at surface brightness variations. It shows surface brightness variations very nicely, but it's not good for looking at very faint things. To look at very faint things, we got to go to Z scale. So watch, this is going to make it pop out a lot more. So if we do that,
Boom.
Oh.
yeah. So the faint point sources pop out a lot more when you go on Z scale.
Sure
That's what that is right
does.
there.
It's at the bottom of the galaxy.
Yeah. So if I were to go back to the galaxy, like the one here in this top left-hand corner, it's going to be kind of all like smear. It's all going to be saturated out. You can't see that detail, but you can see many more faint things.
Sure.
But yeah, there's lots of galaxies out there, and yeah, there's a poet who wrote a poem about like reading by the light of the galaxy, reading newspapers by the light of the galaxies.
Light of the Milky Way, I'm guessing.
No, it's not light of the Milky Way. He said light of the galaxy. So I'll pull it up.
Light of the galaxies. Yeah, so Joanna, just following up on your question, yes, so the dark circles at the bottom of that galaxy, yes, we're thinking those were it could be either the like dust lanes in the galaxy, in the spiral arms of the galaxy. That's probably what those two dark circles are at the bottom of that image. Yes. Check it out.
And we need a galaxy person on speed dial here.
We do need a galaxy person. And in fact, the founder of Shadow the Scientist, Raja Guhathakurta, definitely studies galaxies. He's not with us this evening, but maybe we can ask him this question. It can come on, and when he's on All Space Considered, actually later this month in 2 weeks, Raja's going to be one of the guests on All Space Considered, of which Laura-May is one of the hosts of that show. So maybe you can bring it up.
Yeah. To show him the image and you're like, what's this?
Yes, yes.
We only know rocks. Rocks and comets.
Yes. I'm going to put a link to Griffith Observatory's All Space Considered show page so that you can check it out. It's every third Thursday of the month. Yes.
We like to make it hard to pronounce. Thursday.
Third Thursday. I did have to stop and pause.
It used to be first Fridays. It is now third Thursdays.
First Fridays, third Thursdays. Yes, yes. Slight tongue twister. All right, let me drop that in the chat. Okay, Joanna, I hope that answered your question. Thank you. Okay. Okay, so let me drop that link to All Space Considered here. And again, questions? Yes, okay, great. Thanks, Joanna. I appreciate the feedback. Amazing. Okay, let me put that link in the chat for you now. Okay. Yes, someone mentioned that the image in the article the link that I put there, that article is Neptunian Trojan asteroids exist in broad spectrum of red color, astronomers find. And yes, you're right. The image in the article is the image that that Bryce gave me to use to promote the session. So yes, great job connecting those. Absolutely right. And it is beautiful. It's a multi-band image of the Neptunian Trojans, and you can see the ones that are listed there. And this was taken with the Palomar 200-inch, Gemini, and Keck telescopes. Yes. Okay, thanks. Thank you for that. All right, now let me get back to putting that link for you in the chat. Okay. Okay, there we go. Whoops. Copy URL. Okay. Ooh, all right. Amazing. Thank you, Annalise, for the question. I will get to it in just a moment. Let me go ahead and drop this link in the chat first. And you know how much we love your questions and comments, so please keep them coming. Okay. Oh, well, that is not the right thing. Let me try that one more time. Okay. Now I have the right link, you all. Sorry about that. There we go. Okay. Oh, yes. Great question, Annalise. So the question is, does the addition of ever increasing satellites make an impact on your observations
No,
in
not,
any way?
no, it doesn't. Not currently. And it's not clear when it will.
But that's for us. I mean, this is a topic of broad discussion in the community.
Yeah.
There were a lot of talks about it. The figure I got from someone in the field was that up to 40% of Vera Rubin's data could be heavily contaminated by 2030, 2035. Check that figure. But it is a source of concern, especially for deep sky objects, is my understanding.
Sorry to interrupt. But here is the line from the poem. It's from a poem called Ayers Rock Uluru, which I think is the Aborigine name for Ayers Rock. And it's from a section of it called Throughout the Yellow Journalist. I'm not sure what is mean by that exactly. But he is saying here, so it's by Allen Ginsberg, who is a beat poet. And this is just what he says. He says, out into the Buddha fields, among stars to wander, forever weightless, without a headline, without thoughts, without newspapers to read, in the light of the galaxies.
Wow.
Beautiful.
Can you send that to me?
Sure. And sorry, it's not that I don't like the discussion of the satellites or so on. It's just that there's a lot of talk about it, but not a lot of action.
I mean, I will say that I think talking about it is important for the general public who doesn't really know about this. What are we going to?
So I'm going to move the target to, we are going to move the target to 613490.
Okay, 6134.
And the time is 7 UTC. So please slew when you are
Did you
ready.
do a dark, quick dark?
Put the dark filter in? Yeah, I'm gonna do a quick dark. Yeah. Yeah. So long story short is satellites don't impact have never impacted my observations. Like maybe once low Earth orbit satellite, or just kind of trailed across 2 or 3 degree wide image in about 30 seconds, just shot across, and it was like fairly bright. But my observations, like tonight, we've yet to see a satellite.
Annalise has just kind of a follow-up. She said she sent a link, darksky.org, or trying to promote some form of addressing this issue.
Talking to your Congress people is if you have spare time, and making sure that they're aware, and support politicians who care about astronomy. And
so the American Astronomical the American Astronomical Society has put out reports on this for probably the past decade, as Bryce was saying.
Yes.
And they had a really cool campaign back in January. They had a whole bunch of postcards. A lady called Ruhi, I think, and Colin, they were organizing it. So they got a bunch of us to actually write postcards.
Yes.
And to defend science, for example, or dark skies. And just sending that to, the public address you find for your senator and representative for any issue that you care about.
True.
Is very, very effective.
And Elise says she looked at the pan-star field of what you were observing. And yeah. And she said, of course, your resolution is far better than hers is. But yes, Annalise.
The Pan-STARRS is actually a really nice catalog. Now, so I'm imagining you have Aladdin up. If you have Aladdin up, compare that to the Deep Sky surveys. See the huge increase in sensitivity and resolution. And so Pan-STARRS is, and you can do that on anywhere in the sky, I think above -30 declination, if I'm not mistaken. Maybe it's -40. But that is an incredible advancement. If y'all want to hear my, walking in the snow for 5 hours every morning to get to school kind of story. Okay, so I think we're on target here. So I'm going to start at box 5. Here we go. 613490.
Right.
So it used to be in the old days that to do what we're doing, you would want to get an image or some idea of what the field containing your asteroid looks like. And so in the old days, you would have to do something like go to a library, and you would look up something called the Palomar-Leiden Survey, which is actually really, really good. So, but they have plates. They took photographic plates that are about 7 angular width-wise. They're about 7 degrees wide, and they would map the entire sky, I think, above -20 declination. Oh. And so what people would do is they would literally go to the library, and they would look up the catalog. And so the catalog was organized in RA and declination. So they would look at the images. They would find the RA and dec closest to their target, and they would take the image plates out of the catalog, and then they would find which point specifically on that image plate that their target was near, and then they would take a picture of it with like a Polaroid, like with those instant exposure, take to develop. And then they would take that picture with them to the telescope, and they would look when they take the picture, like kind of what we're doing.
Wow.
And they would like twist it around. And so I came onto the scene in astronomy well after that era, thank goodness. But we didn't have Pan-STARRS yet. We had the Deep Sky Survey, which is a collection of from a bunch of different surveys. And so I'm guessing you can you can see, if you have Aladdin up, the difference between the Deep Sky Survey, and there's also Sloan Digital Sky Survey, but Sloan Digital Sky Survey covered a much smaller extent. Deep Sky Survey is northern and southern hemisphere, and SDSS was northern hemisphere only, and in a very small area. So you have like a very limited area where you could like look up your fields. Or you had to use a Deep Sky Survey. So, but like Pan-STARRS is much higher resolution than Deep Sky Survey, and much deeper as well. It goes to about 22.5, 23. I think in some cases more than that. So I'm very thankful to Pan-STARRS. It's made this business a lot easier.
Mm.
And Rubin, it's in the southern hemisphere, so it's going to cover -90 to I think +20 or +30 degrees declination. So it's going to provide that for some of the southern hemisphere, but much higher resolution and much deeper limiting magnitude. No, we are not. We are observing on Tuesday, but at a different telescope.
Oh, okay. I suddenly have to go.
Yeah. It's nice to have
For
you.
joining us.
It's nice to have you as a
Miss
surprise
Ava
guest.
from the software team.
Instagram.
Yes.
So if you're there, just let me know where you're at. So
Oh, okay.
Okay.
Oh, well, before you go, give me your Instagram too.
Yeah.
Sorry, I'm so tired. I've been up.
No.
Oh, of course. So we're all going to get Ava's Instagram now.
There you go. Yes. Okay, so the good news is we're in a very, very clean patch of sky here. We just got our first wideband image. We're taking the second wideband image. But the good news is that our target is in a very, thank you so much.
Yeah, I'll see you guys.
See you.
Okay, see you.
Bye.
So glad to
Is it Ava spelled with an A? A-V-A? Ah, okay. I thought you were
I'm so
Evie.
sorry. Yeah.
Yeah, I was saying your name wrong the entire time. It was,
Okay.
sorry.
I don't think you were.
Ava.
Oh.
Okay, Ava.
All right, well, it's
Thank
nice
you.
to meet you, Ava.
Yeah.
See you.
Okay, aloha.
All right. So yes, so this is so we're actually in a very nice part of the sky here. It's not dense with stars, which will make things easier to find. Might make calibration a little bit more difficult, but the good news is we don't have to worry about our source being on top of a star, and we got like a nice field, and it'll be easier to recognize because we won't have to confuse it with any nearby stars. So yes, we have this object is moving north, kind of northwestish. So I think we don't have to worry about wandering into any stars either, but it's moving very slowly at a rate of about 0.01 arc seconds per minute.
Oh, thank you, Annalise. So Annalise says, in regards to the old methods, she says, I still have uranometria in star catalog and other star catalog books. We took the photocopies and reversed the images. And so she says, I'm used to doing it with star maps. Oh, wow.
So that's the way you had to do it.
Nice.
And it's not a bad way because what you would do is you would just look for asterisms with the brighter stars, and you would try to measure the angular distance in the coordinate region between the brighter stars. So it's not necessarily like a deal breaker if you can't use the Pan-STARRS, but Pan-STARRS makes things a lot easier.
It does make it easier. So okay, and Annalise does have Aladdin up, and thank you for sharing your Aladdin link. Let's look here what you're seeing. Okay. Okay, and so she says that she zoomed in with the coordinates that you gave, but you can only get a few of the anchor stars.
That's right. You call them anchor stars.
Yeah.
Right, that's right. Okay. Thanks for checking it out, Annalise.
So we're about to get our first wideband image of this object with an air mass of, let's see where it's 1.16. So that's pretty low. And when we finish, the air mass should be, I would say, maybe 1.3, so also not bad. So I think we're making good progress here.
There we go.
Alrighty. So now I'm going to do before and after.
Here we
We're going
go.
to do the before here, and I'm going to set up the after. So we have before, after, and we're going to play the game. Yeah, so you can see a lot more stars pop up this time.
Yeah.
Now, if you have your Aladdin now, the Arian deck you want to use is, do you want to type this into the chat window?
I do. So this is the
I'll
coordinates.
text it to you, so you can just, if you have it on your phone, you can paste it just into the chat window
Thank you.
from your text messages. So I just texted it to you.
Perfect. Got it.
But it's 354.50.3 in RA and plus 130404 in declination. If you want to follow along at home.
Oh, that's fun.
Yeah.
Okay, so I'm putting the coordinates of this new target in the chat right now.
That's right. Okay, so I can see in the Aladdin, I can see these 4 stars here. They're very faint in Aladdin, but they barely appear, but they kind of form an arrow and they point towards the asteroid, which is in between this bright star and this kind of arrow point here. So I think that's the asteroid right there.
Right there.
That one right there.
Mm.
This is in wideband, so pretty
Little blob.
pretty good throughput.
Yeah, it looks pretty good. It's bright.
Thank you.
Yeah, that is nice.
This one has a smaller inclination, by the way. So this one is
Oh.
8 degrees of inclination.
Oh, big difference in the previous
Big
one.
difference.
Yeah. Mhm.
You mentioned that it was found on Sloan Digital Sky Survey from Apache Point.
Oh,
Apache Point, not very famous.
I
but an
don't
amazing
know
observatory.
if I don't know.
Put
who
that in the
discovered
image.
this object. Let's see.
It's Apache Point.
Let's see. Neptunian Trojan.
which, oh yeah, Apache Point was at the American Astronomical Society
They
meeting.
were there.
Yeah.
Yes.
They gave this amazing gift that I'm so excited about. I'm gonna frame it. It is part of the mask. So these little metal plates that have been drilled to match certain objects.
61349.
And so they gave away little parts of it that were used for this Sloan Digital Sky
Yes.
Survey. And this is a super important survey for astronomy. So I feel like
Yeah.
it's such a really cool little object.
Nice.
Yeah, so this object was discovered at a magnitude of 22, so that is pretty bright. That is
Yeah.
pretty bright. So that would be in the range for Apache Point.
Okay, I'm putting a link to Apache Point in the chat.
Yeah, the thing looks like a box. It's a telescope that looks like a box, like a cargo container.
Cargo container. It's pretty big as well, from what I recall.
Yes. Yeah, so I guess if you were really floating around in space, all you would have, the only source of light you would have to read newspapers by might be the light of the galaxies.
Right,
So,
right.
yeah, just, if you're in intergalactic space.
I hear about people who can read or see their shadow from the Milky Way. I mean,
Just
I worked at
heard
Grand
that.
Canyon, I did not get to see that, even though they have an amazing sky. So I don't know. I look forward to seeing that perhaps someday.
Yeah, I think you have to be in a very dark spot. Dark sky.
I don't even know if you could see it at Keck Summit.
Maybe if you're in the southern hemisphere where you have
Yeah.
the galactic core going overhead.
True.
Not exactly overhead, but because you wouldn't have a shadow, right?
Right.
Has anyone here seen a Lahaina noon?
I've always
Oh.
wanted to see one.
I have.
That's amazing.
It's a well, actually, before I say that, do you want to tell us what Lahaina noon is while I'm putting something in the chat?
A Lahaina noon is when the sun is directly overhead, like exactly at zenith, 90 plus positive 90 degrees, so that you don't have a shadow. You have, if you were to put a pencil up or like this water bottle up.
Yeah, it's just
So like this water bottle casts a shadow
directly
on because the light source is a little bit diagonal, and casts a shadow on the desk here. But you would Lahaina noon is where you would see this. You would put this water bottle on the table, and it wouldn't cast a shadow at all.
There's several passes. May 18th for Big Island, where we are now, to May 31st. And for the mid-July, it's July 11th to July 24th for Big Island.
Oh, that's
And also, if you go to Honolulu, there's this beautiful sculpture that was made to celebrate commemorate
There's a
Lahaina
Lahaina
Noon.
Noon sculpture.
Oh, I have
It
not.
looks
seen
like
that.
I don't know, like a eyeball kind of like
It's like a
it's like
big
an
kind of
outline
series
an
of.
eyeball.
It almost
Huh.
looks like a modern Stonehenge. I feel.
Yeah. That's
Oh.
You know, like it's these pillars with this
But-
cool circle.
Yeah, it's supposed to make like a unique pattern on the ground when the
Yeah.
Lahaina Noon is ongoing.
Now you can look up
Right.
cool images of Lahaina Noon, and it really looks like a weird Minecraft rendering of like pillars and objects that don't have a shadow. It's really cool, and it doesn't occur everywhere on Earth, obviously. So you have to be somewhere where that can actually happen, and your location will land where the sun will be directly overhead. There's a very beautiful and important poem in astronomy. It's fairly well known. It's called Planetarian by Adrian Rich, and it is about Caroline Herschel. Caroline Herschel is the sister to William Herschel. And did William Herschel discover Uranus, or is it another Herschel?
No,
It
that
was
was William
yeah,
Herschel.
Yeah.
Actually.
She discovered tons of comets. She actually was a huge help on all of his observations in her own right, but she was not credited because at the time she was a woman. And
She has a very interesting headdress too. If you look her up.
Oh, I didn't know that.
Yeah, she has a very
I'll drop a link
But
in the chat.
I will drop you the link now.
Yes,
It's a
okay,
very beautiful
Laura-May's
poem
gonna
about
send it.
astronomy as well.
Yes, okay, there it is. And so now 2 poems. Wait,
I
I
know,
think
right?
this is the first time that we've talked about
poetry.
astronomy related poetry on Shadow the Scientist. Yeah, love this. Let me do that.
And if you want to go hardcore sci-fi poetry, in that
Yes.
space, there's an extraordinarily long poem. It's a sci-fi epic poem called Anyara by Harry Martinson. And it was turned into a sci-fi film about, I want to say, 5-6 years ago.
Oh,
I will warn you, it's a little depressing.
uh-oh.
It's set in the future, and it's a ship that's supposed to just take people to Mars, and then they veer off course and they can't turn back, basically. And so they're wandering interstellar space on this cruise ship, basically. But it's a pretty interesting, if you want a longer read, it's a long sci-fi poem about space called Anyara, and it's translated from Swedish.
Ah, thank you.
of
Thank you,
course.
Laura-May. Yes. All right, we'll see you next time. Take care. Aloha.
Aloha.